So how are we going to calculate the execution or running time of an algorithm, which we denote as T of n, the time function? So in this lecture, we're going to discuss on how to calculate the running time of an algorithm or program. Say for example, we have an algorithm or a program with m instructions, like we have instruction 1, instruction 2, instruction 3, up to instruction m. So say this is the algorithm or the program consisting of m instructions or statements to be executed. So what is then now the total execution or running time of the algorithm or program with m instructions? How do we calculate for the total execution or running time? The total running time of the algorithm or program is simply the sum of the running time of all instructions or statements. Say we denote I1 as the running time of instruction I1, and then I2 is the running time of instruction I2. Since it is sum of the running time of all instructions, then T of n, which is this, is simply equal to running time of instruction 1 plus running time of instruction 2 up to the last running time of instruction m. So it is simply this one. That is the total execution or running time of an algorithm or program having m instructions. We can simplify that into this mathematical expression. So it is simply the summation of ij, where ij is the running time of instruction ij. So it's the sum of all ij, where j is from 1 to m. Okay, thus we have this in our formula. So where ij is the execution or running time of the jth instruction, and where j is from 1 to m, and m is the total number of instructions in the algorithm or program. And so if we are looking for the value of this, then we need to know each of this, right? Because this is equal to the sum of all ij. So the next question would be, how do we find the value of ij, or how do we compute for the value of ij, or how do we compute for the running time of one instruction j? Now, to compute the running time of one instruction, we need to know the values of two items, xj and yj, where xj is the amount of time to execute instruction j, and yj is the number of times the instruction is executed. So it is called the frequency count of an instruction. So yj is called the frequency count. The frequency count of an instruction, or how many times it is executed. How many times it is repeatedly executed. While xj is the amount of time to execute that instruction. Okay, so the amount of time to execute that instruction times how many times it is repeatedly executed. Okay, that's the total running time of the instruction, ij. And when you find the value of I1, I2, I3, I4 up to IM, then you get the sum of that. That is your total execution or running time of the whole algorithm or the whole program. So from our previous discussion, we found that the running time of one instruction ij is simply the product of xj, the amount of time it takes to execute this instruction, times the number of times or the frequency or how many times it is repeatedly executed. And that is your yj. So again, the running time of one instruction, ij, is equal to the product of xj, the amount of time to execute instruction ij, multiplied by how many times that instruction ij is executed, or the number of repetitions. To find the value of ij, we need to know these two values, right? But the question is, can we determine the value of xj? Instruction printf, for example, hello world. Say you run this in an i3 processor. Do you think the exact running time of that is the same when you run it in processor i7? That same instruction. So the running time of this instruction is dependent on the speed of the processor, or the hardware specification of the computer, right? As we have discussed last time, there are 5 factors that affects the running time of a program or an algorithm. And one factor is the computer hardware specifications. So if you are running that program in a fast high-speed processor computer, then the running time would be lesser compared to when you run it in an old computer with a slow processor. So for one instruction like this one, you can never determine a fixed, or you can never assign a fixed running time for one unique instruction. So again, you can never determine the exact running time of one unique instruction. Why? Because you may run it in different computers, okay? And different computer specs will result to different running time for that one statement or instruction. So this is not possible for us to know. And therefore, the running time of one instruction ij is approximately equal to yj. They cancel out the x. So what determines the running time now of an instruction is the frequency count, yj. So running time of one instruction is now dependent only on the frequency count, or how many times it is executed. The reason for that is since we cannot exactly determine the value of x because it is machine dependent. So the formula of computing T of n is now simply y1 plus y2 plus up to ym. We call this the total frequency count. X is no longer part of the equation. So instead of originally that is simply x1 times y1 plus x2 times y2 plus dot 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 plus xm times ym, right? Since we remove the x from the equation, that is now simply this one. Okay, y1, the frequency count of instruction 1 plus the frequency count of instruction 2 plus up to the frequency count of the last instruction. T of n now is just the summation of yj, where j is from 1 to m. So with that, let's take a look at these 3 examples. We have an algorithm with only one instruction labeled I. Okay, this is to increment x by 1. What is the frequency count of this? It's just 1, right? T of n here is 1. In the second example, the code consists of 2 lines. When you trace a program, you are executing the program line by line. You will see which line of the program or code is executed because the line is highlighted, which means it is the one being executed at the moment. And so, the number of times the line is visited or highlighted is the number of times it is executed, or we call it its frequency count. In the case of the second example, there are 2 lines. Let's label the first one as L1 and the second line as L2. And take note that this is a for loop. And the number of iterations of this for loop is n, right? Because the loop variable I is from 1 to n. And assuming that n is a positive integer, then this for loop will iterate n times. So number of iterations is n. That is when I is equal to 1 up to I equal to n. Now, if say for example n is equal to 5, then your I is from 1 to 5. There will be 5 iterations. Okay? So when we trace this line is first highlighted. That is the time when I is set to 1, and then we check the condition. It is true, and therefore this is executed. Okay? So how many times is this statement in the loop body executed? If the for loop iterates 5 times, then this is executed 5 times also, right? And this one, this line here, L1, is executed 6 times, okay? So the for loop heading is executed number of iterations plus 1. Okay, n is the number of iterations, and then plus 1. The plus 1 there is when I becomes 6, and then the condition is now false because 6 less than or equal to 5 is now false. So that this line here is executed n plus 1 times, and this line here is executed only n. Okay, take note that the for loop heading is always executed one more time than the statement in the loop body. Okay, so this is number of iterations n, and the plus 1 here is when the value of I exceeds the upper limit, which is n. Okay, so when I becomes n plus 1, okay, when we increment I, then that's the time the condition becomes false, and this will no longer be executed. Okay, so L1 is n plus 1, the frequency count, and L2 is n, so you add it. So T of n for the second example is line 1 plus line 2. That would now be 2n plus 1. That is why in our answer here, that is 2n plus 1. So again, the frequency count of the for loop heading is number of iterations plus 1, while each statement inside the for loop is simply number of iterations. So since this iterates n times, I is from 1 to n times, so that's why this is n, the frequency count of the second line, and the frequency count of the first line here is number of iterations plus 1, so n plus 1. That's why this is 2n plus 1. Okay, the sum of the frequency count of L1 and frequency count of L2. Now, how do you get the number of iterations? How will you determine the number of iterations? Now, for this example, it is easy because you start with 1, okay? So when you start with 1, then the number of iterations is n. That is assuming that n is included in the range, okay? But if it's not 1, say for example, if it's like this, for I from 2, I less than or equal to 8, I plus plus, how many iterations are there? How do you get the number of iterations? It will be upper limit, which is this 8, minus lower limit 2 plus 1. That is the number of iterations. The formula for getting the number of iterations is upper limit, this one, minus lower limit, or the lowest value, the highest value of the loop variable, minus the lowest value, plus 1. Okay, so that's highest value or upper value, upper limit, minus lowest value or lower limit plus 1. So in the case of the second example, when your I is from 1 to n, the upper limit or the highest value of I is n. So we say n minus the lower limit is 1 plus 1. Okay, using this formula, then cancel out these two, the answer or the value for number of iterations is n, and indeed it is n, right? So in the case of this example, when I is from 2 up to 8, so that will now be 8 minus 2 plus 1, that gives you what? 7. 7 iterations, okay? That is from I equal to 2, 3, 4, 5, 6, 7, 8. There are 1, 2, 3, 4, 5, 6, 7 values. And so that is the number of iterations. Now the third example, which is this, there are now 3 lines, okay? The first line, say we call this L1, the second line, say we call this L2, and the third line is this, okay? So we have here a nested for loop, okay? A for loop inside a for loop. This is the inner for loop, and this is the outer for loop. Inner for loop, this one here, and this is the outer for loop. Now, the outer for loop iterates how many times? The control variable of the outer for loop is I, and that is from 1 to n. So this is the upper limit and the lower limit, or the highest value of I and the lowest value of I. So from that formula we have a while ago, highest value minus lowest value plus 1, right? That's the formula for getting the number of iterations. So by that, we would say that this would be n minus 1 plus 1. And so the number of iterations of this outer for loop is n, okay? But remember that this is a for loop heading, and what is our formula for the frequency count of the for loop heading? It is number of iterations plus 1. Number of iterations plus 1 for the for loop heading. For the loop statement inside the loop body, it is simply number of iterations. Okay, only number of iterations, while for the for loop heading, it is number of iterations plus 1. Okay, there is a plus 1 there because this is the time when you go back to the for loop heading to increment the loop variable, and when you check the condition, it is found to be false. And since that is false, the loop statement in the body are no longer executed, but the for loop heading is executed plus 1 times. So there's always one more execution for the for loop heading compared to the loop statement. So since this is a for loop heading, the frequency count is number of iterations plus 1. So it will be n plus 1. And for the second line, L2, the inner for loop heading, if we forget about this, by itself, basing on this formula, that would be number of iterations plus 1, right? So just looking at that, how many iterations are there? It's the same as the first one, right? 1 to n. So since that is 1 to n, the number of iterations is n, right? So it is n plus 1, again, because it is a for loop heading. The control variable of the inner for loop is j, and from here you will see that the lowest value of j is 1 and the highest is n, okay? So the number of iterations of this inner for loop would be n minus 1 plus 1, which is the same as the outer for loop. It is n. It is n plus 1 because the plus 1 there is when j is incremented and the value of j exceeds n. Okay, that is when your j becomes n plus 1. So this is executed at that time when j is n plus 1, but this is no longer executed. So by itself, it is n plus 1. So let's write it here. L1 is n plus 1 and L2 is by itself is n plus 1. Now since it is inside this outer for loop and this outer for loop iterates n times, so you have here times n. This is with respect to the outer for loop and this is with respect to itself. So if this is just alone without this, the frequency count of this is n plus 1. Now since it is inside this outer for loop, times n because the outer for loop iterates n times. So each of the statement inside this outer for loop will be n times whatever is the frequency count of itself. So that's why we have here n times n plus 1. And that is why in our answer here for L1, it is n plus 1. And for L2, it is n square. Okay, you get the product of n and n plus 1. That would be n square plus n. And the last line, L3, by itself, just like example 1, by itself, the frequency count is 1. Okay? Since it is inside the inner for loop, this one, that iterates n times, so you have here n times 1. But it is still inside the outer for loop that iterates n times. This outer for loop iterates n times, the inner for loop iterates n times. Therefore, you'll have another here, another n there. Okay, so this is with respect to the outer for loop. This is with respect to the inner for loop. And by itself, it is count 1. And so, this is now n square for L3. And so you add all of these three lines. So T of n now for the second example would be L1 plus L2 plus L3. That is simply what? N plus 1 plus n square plus n square. So what is that? You have 2n square. So 1, 2. That's why you have here 2n square. And then you have n and n here. That's why you have 2n. And the last remaining is 1. Okay? So the frequency count of the third example is 2n squared plus 2n plus 1. And notice that the frequency count of the first example, which is simply 1, is a constant value. And the second example, frequency count T of n is 2n plus 1. This is linear. If you're going to plot this in the Euclidean plane or xy plane, this would be a straight line. While the third example is quadratic. Okay, this is a quadratic expression. The next example we're going to discuss is a program that generates the Fibonacci series. In mathematics, the Fibonacci series is a series of numbers such as this, which starts with initially two numbers, 0 and 1. The next number in the series would be computed by getting the sum of the previous two numbers. So this is 1 because the sum of the previous two numbers is 1. 0, the first number, plus the second number is 1. So 0 plus 1 is 1. That's why this one is 1. The next number is 2 because the sum of the previous two is 1 plus 1. It gives you 2. The next number in the series is 3 because the previous two numbers are 1 and 2, and getting the sum of that, 1 plus 2, that is equal to 3. The next number in the series is 5 because the previous two numbers are 2 and 3. You get the sum of that, it gives you 5. The next number in the series is 8 because the previous two numbers are 3 and 5. When you get the sum of 3 and 5, it gives you 8. The next number in the series is 13 is because the previous two numbers of 13 are 5 and 8. 5 plus 8 is equal to 13. That's why this is 13. Now guess what would be the number after 13? It would be the previous two integers or numbers are 8 and 13. So 8 plus 13, that gives you 21. So the next number after 13 is 21. So how is this computed? We have here the code or the program that computes this series of numbers. This program is written in C programming language, and it starts with this statement, the scanf, which asks the user to input the value of n, or how many numbers in the series it should generate. Now, we have two cases. Case 1 is if the input value for n here is less than or equal to 1. That's case 1. The second case is if the input value in here for n is greater 1. So that's case 2. Under case 1, n is less than or equal to 1. So the value of n would start from negative infinity up to 1. Okay, so the biggest value or the largest value in this range, or in this case 1, is 1. And for case 2, it is when n is greater 1, the smallest number in this case is 2 because it is n greater 1. So n greater 1, the first smallest number would be 2, and then 3, and then 4 up to positive infinity. So in the code, case 1 is this if block. So this is case 1. So when this is true, then that is case 1. And case 2 is the whole else block, which is from that up to here. Okay? This is the beginning marker of the else block and the end marker of the else block. And this is the beginning marker of the for loop, and this is the end marker of the for loop. The else block is case 2. Case 2 is when n is greater 1, and case 1 is when n is less than or equal to 1. So say for example, the user inputs a value 1 in here. When this condition is evaluated, it would result to true. And since that is true, this is executed. And the whole else block will not be executed. That's why under case 1, when we run the program, this instruction will have a frequency count of 1. And then after that, this is evaluated. So this part here is frequency count 1 also, meaning this scanf is executed once. And then after that, we execute this part, which is to evaluate the condition if n is less than or equal to 1. Okay, so that's one execution. And when this condition is true, then the next line, which is the printf, is executed. That's why you have here 1 frequency count. And since this is true, because n is less than or equal to 1, then the whole else block, this whole part here of statements, will not be executed. That's why the frequency count of these lines are zeros. So under case 1, when n is less than or equal to 1 in here, this is true. So this has a frequency count of 1 for this line, and this line has frequency count 1. And since that is true, this has a frequency count of 1, meaning it is executed, and all the rest of that will not be executed. So it will have a 0 frequency count. So if we're going to get the total frequency count, meaning you add all the frequency count of all the lines or all the statements, you have 1 plus 1 plus 1, you have 3, right? Let's say we call this T1 of n. The first total frequency count is equal to 3, which is a constant. Whatever the value of n is, as long as it is less than or equal to 1, if n is equal to 1, or if n is equal to 0, or if n is equal to negative 1, any value to the negative infinity, any of these values where n is less than or equal to 1, that's case 1, the total frequency count or the running time of the program is approximately a constant 3. Under case 2, that is, if the value of n that the user inputs in here is greater 1, so this is executed. So you have a frequency count of 1. And then after that, this condition is evaluated. So this line here is executed. That's why you have here a 1. And since this is false, because we are now under case 2, the values of n are 2 up to positive infinity. So this is false. And therefore, the third line or the third statement is not executed. That's why you have here 0. It would then jump to executing the first statement inside the else block. This is not executed, so that's why it has a 0 frequency count. Because the else keyword and this open marker, they are not something to be executed. They are just control markers. So when the condition is false, this is not executed, and it jumps to execute the first statement, which is this one, assigning the value 0 to the variable fnm2. So this is executed once, and the next statement in this line is this, so another one execution. So a total of 2 executions. Why 2? Because there are 2 instructions or statements in this line. One execution for that and another one execution for that. So it has 2. Next is the for loop heading. Now recall from our previous example that you need to get the number of iterations of the for loop. So what is the number of iterations? Take note that the loop variable I is from 2 up to n. N is included because this is I less than or equal to n. So n is included. So your loop variable I is from value 2 up to n. So the number of iterations would be n minus 2 plus 1, right? So that gives you how many iterations? Minus 2 plus 1 is minus 1. So n minus 1. N minus 1 is the number of loop iterations. And since this is a for loop heading, the frequency count of a for loop heading would be number of iterations plus 1, right? From our previous example. So that would now be n minus 1, the number of iterations, plus 1. That gives you, cancel this 2, simply n. That's why we have here n. Okay, that's n for this for loop heading line, this one. And the frequency count of each statement inside the for loop would be the number of iterations. So for this statement, it would be the number of iterations, which is n minus 1. And this would be n minus 1. This would be n minus 1. That's why this line is n minus 1, this is n minus 1, and this is n minus 1. And then we could count that as 0 since it is just a end marker. Now after this is executed, the for loop, this printf here will be executed. And the frequency count of this is the same as any of this statement here. So this has 1, executed only once. And these two are end markers, so they just have 0 execution. And so the total frequency count now under case 2 would be what? It will now be 1 plus 1 plus 2. That gives you 4. And this is n plus n minus 1 plus n minus 1 plus n minus 1. So count how many n. You have 1, 2, 3, 4. So you have 4n. And then you have here 1, 2, 3 minus 3. And you have here plus 1. So that gives you 4n. This is 4n. And then you have 4 plus 1 is 5. And then the minus 3 is this one. So now you have 4n is this one. And 5 minus 3 is 2. So the total frequency count now is 4n plus 2. The first case, let's just denote this total frequency count as T1 of n is 3. As mentioned a while ago, is a constant running time, while this one is said we denote that as T2 of n, 4n plus 2. And this is a linear running time. Now, the O of n denotes a more general approximation of the running time or the performance of the algorithm that measures not just the time complexity but also the space complexity. And we will discuss that in more details in the succeeding lectures. So, which of these two cases is the best case and the worst case? Of course, the best case is 3 because T1 of n, which is 3, under case 1 is less than the T2 of n, which is equal to 4n plus 2 under case 2. But we have to prove it mathematically, okay? So this is still a question mark that needs to be verified. So verify if indeed the case 1 total frequency count T1 of n, which is equal to 3, is indeed the best because it is less than the case 2 total frequency count or running time, which is 4n plus 2. So to verify, we would say case 1 is 3. Is it indeed less than case 2, which is 4n plus 2? Now, n is a variable, so we need to substitute a value in place of the variable n. Now, this is case 2, so take note that the values of n for case 2 is from 2 up to positive infinity. So let's say we take the smallest value, which is 2. So this will now be 3. Is it less than 4? N is equal to 2. So substitute 2 here. So 3. Is it less than 4 times 2 is 8 plus 2? Yes, 3 is less than 10. Okay. So we conclude that case 1 is the best case and case 2 is the worst case. When we say best case, that is the case when the program or the algorithm takes shorter time to run. And the worst case, which is case 2, that is when the program takes longer time to run.